Hi everyone. Nvidia has dominated the GPU market for training deep learning models, but now Amazon is quietly challenging this dominance. Amazon is producing millions of its own powerful AI accelerators, delivering comparable performance at a quarter of Nvidia's cost. Anthropic, the AI lab behind Claude, has already committed to training its next generation models on Amazon chips, specifically 400,000 of them. Is this the beginning of the end for Nvidia's monopoly? Keep watching to learn more. This video has 3 parts: Anthropic's partnership with Amazon, building custom chips, and breakdown of Amazon's AI accelerators. Part 1. Anthropic's partnership with Amazon. Anthropic is probably the most famous AI frontier lab outside of OpenAI. Anthropic produces an AI product called Claude. The URL is claude.ai. It's better than ChatGPT at most programming tasks. And in fact, their latest model, Claude 3.7 Sonnet, is actually specifically optimized for programming. Of course, you can use Claude for anything, just like ChatGPT. You can ask it arbitrary questions in text, ask it to reason through things for you. But a real key target market for Claude seems to be software developers. Using Claude 3.7 in combination with Cursor seems to be the favorite AI-assisted programming environment on the internet right now. In fact, this type of setup has become so popular amongst developers that Anthropic's revenue increased tenfold in 2024, reaching $1 billion by December. Most of the AI labs these days have a big partner that has really deep pockets to actually fund them. For example, OpenAI raised $10 billion from Microsoft, and there was a close partnership there for a while, although they seem to be sort of going separate ways now. DeepMind, of course, is backed by Google, and Anthropic needed to find their own partner to get access to lots of cloud GPUs and funding, of course. They found Amazon. Amazon is the primary cloud provider for Anthropic, and they have invested $8 billion of their own into the startup. Anthropic has a lot of other investors, though, too. Even Google put $3 billion into the company. And earlier this month, as of the time of this filming, Anthropic just closed a Series E funding round for another $3.5 billion, which makes them valued at $61.5 billion. So obviously, Anthropic is not hurting for money. Let's break down the money that Amazon has given to Anthropic. I said $8 billion, and that has come in 2 tranches of $4 billion each. The first $4 billion came with the string attached, or the benefit, however you look at it, that Anthropic would use Amazon as its primary cloud provider. And the second $4 billion had a much more interesting string attached, which was that Anthropic agreed to use Amazon's chips rather than Nvidia GPUs for training its future models. Up until now, Anthropic has used Nvidia chips the same as everybody else, A100s and H100s primarily. And you may not even have been aware that Amazon was making AI accelerator chips, but apparently they are. And Anthropic is the biggest and most important customer that has been convinced to start using them at this point. Specifically, Anthropic will be using the Tranium 2 chips to train their models. Yeah, it's kind of a funny name, but we'll go into Amazon's naming scheme in a bit more detail later. This is actually a big ask for Anthropic because they're not going to be able to use CUDA. They're not going to use the standard software stack that they're used to with NVIDIA. But I guess having really close ties with the company that's actually producing the chips and has a vested interest in you ironing out the bugs in their software stack will be in their favor. This isn't just an agreement on paper either. Amazon is currently building a cluster for Anthropic. This cluster is being built under the codename Project Rainier, because Amazon is based in Seattle, I guess. The cluster has 400,000 Tranium 2 chips, and it's being built in Amazon's new Indiana campus. The campus is being built in 2 phases. The first phase is complete, and they have 7 buildings, each of which has 65 megawatts of power. After the second phase is complete, they'll add 9 more buildings of the same capacity for a total of 1,040 megawatts of power, just over a gigawatt. And of course, the campus is going to have NVIDIA Blackwell chips, as well as Amazon's own internal chips. They're not putting all their eggs into one basket at this point. But anyway, these 400,000 Tranium 2 chips have approximately the same compute performance as 100,000 NVIDIA Blackwell chips. So when you hear about other AI labs making 100,000 GPU clusters, well, this is Anthropic trying to get on roughly the same level. And for Amazon, they're killing multiple birds with one stone. They're getting a reliable partner to test out their new hardware, and work out the kinks. They're giving Anthropic billions of dollars, but that money is mostly coming straight back to them in terms of paying for cloud computing costs. And it allows Amazon to potentially start making inroads in that GPU accelerator market, which is currently owned by Nvidia. Part 2, building custom chips. As I've already mentioned, Nvidia is dominating the GPU market for data centers, which is what we care about here. Of course, there's the GPUs that get sold to gamers and consumers, but there's also the GPUs that get put into data centers. Those are the higher end ones, and that's what we care about here. Nvidia's market share was 98% in 2023. They basically owned it, but it had gone down to 92% in 2024. So they are experiencing some competition here. And this is mostly due to the fact that cloud providers, especially the largest cloud providers, which we call hyperscalers, really don't like depending on just one supplier. Even if it's a really dependable supplier like Nvidia or TSMC, they want to have multiple options so that if there are any hiccups in the supply chain or whatever, they're not going to be forced into a situation where they have to tell their customers, sorry, I can't give you the hardware that you want. And right now, Nvidia GPUs are super popular. You basically can't buy them. You have to go onto a waiting list. And although the hyperscalers are kind of at the beginning of that queue, they still have to wait to get the capacity that they want. Nvidia just can't produce chips quickly enough to meet demand. So nearly all of the biggest providers are trying to find alternatives. Here's a quick rundown. Google has been building its accelerators called TPUs, or Tensor Processing Units, for years, since 2015, and they've been publicly available since 2018. Microsoft is building special purpose AI accelerator chips called Maya 100, though they seem to be targeted at general AI problems and not LLMs specifically, which some of these other examples are. And finally, Amazon is building its own chips for machine learning inference called Inferentia, and another set of chips for training called Tranium. Yes, very inventive names, I know. We will be focusing on Amazon's chips, of course, in this video. There are other sources, other companies besides the hyperscalers that are also trying to create new GPU hardware. A reasonably big player is AMD, of course, especially in the gaming space, but they also make data center GPUs. There's also Groq and Cerebras. I interviewed employees from both of those two companies previously. You can check out some of the videos over there. They're creating more specialized or unusual designs for inference or really large-scale training. And let's not forget Huawei in China, which is producing its own chips. There are other Chinese companies as well, but they aren't as far along. So given all these competitors, what is Amazon's strategy? Well, they actually have a pretty consistent strategy, not just in AI accelerators, but in hardware in general. They wait until they have quite a lot of volume from customers, and then they try to build in-house versions of chips that they need a lot of. That way, the savings that they gain from having specialized hardware is actually going to multiply out over a lot of different customers. They first did this successfully with CPUs. Whenever customers are renting a virtual machine from Amazon's cloud, it's typically an x86 machine, right? When the CPU would have been produced by Intel or AMD. There are a lot of patents wrapped up in the x86 infrastructure, so basically only those two companies can produce x86 chips. So Amazon went for the next best thing and started to create its own ARM processors. ARM is an alternative architecture that kind of started out in smartphones. Basically all of the Android and Apple devices out there have various ARM processors in them, produced by Qualcomm or Samsung or many others. This is because ARM is much closer to being an open standard, so it's more feasible for other companies to spin up their own ARM processors. ARM processors are also a lot simpler, which is a bonus. And they've been catching on in a big way. You might have seen Apple Silicon, their new M1, M2, and so on processors that are in their actual laptops and desktops. Those are ARM-based processors as well, in this case constructed by Apple. So anyway, Amazon did the same thing. They produced their own ARM processors and put them into servers. This line of processors is called Graviton, and Amazon is on Graviton 4. Amazon can charge less for the servers that are running Graviton processors, and they're hoping that their customers will be willing to migrate from x86-based machines to ARM-based machines, because it might be annoying, but the end result will be cheaper. And I would say it's definitely working. In fact, Apple, which doesn't really have its own big cloud, but rents from other companies, including Amazon, Apple started using a lot of Graviton processors. Again, they probably liked the ARM aspect. They moved, I think, nearly all of their infrastructure over to Graviton servers, and it ended up costing them 40% less. Apple has also switched from Nvidia to Amazon-based chips for some of their inference workloads, and they found it to be about 2x cheaper as well. But here's the kicker. Amazon said that of all of the new servers deployed on AWS right now, 50% of them are on Graviton processors. So ignoring their existing virtual machines, which are legacy and have been running for who knows how long, when customers are creating new machines, fully half of the time, they're using Amazon's own custom-designed hardware. Amazon is obviously hoping to replicate this strategy for the AI accelerators. Again, it's much earlier days, but they do have some customers, including Apple apparently, trying them out. Amazon is even approaching some of its larger customers that have a good relationship with Amazon and saying, hey, you're using X amount of Nvidia compute. We'll give you the same amount of compute, but based on the Amazon Inferentia or Trainium chips, and we'll charge you only 25% of the total cost. So for these companies, if they're willing to put in the time to port their software, they can get a cloud bill that's 4 times cheaper, apparently. So there are some customers that are reportedly enjoying these new chips and the savings that come with it. There's also a 40,000 chip cluster that Amazon is making available to researchers at universities because, again, they just want to increase the adoption of their chips. That's the biggest problem at the moment. They're cheaper, but no one knows how to use them. Part 3, breakdown of Amazon's AI accelerators. You'll notice I keep saying AI accelerators, and that's because Amazon's chips are not technically GPUs. GPUs have a specific internal architecture that's based on being as general purpose as possible, but if you know that you're going to use them to accelerate AI workloads, there are certain optimizations that you can do. We'll talk about the architecture that Amazon chose to use in a little bit. Amazon started building its hardware with the Inferentia, which became known as the Inferentia 1, which wasn't very popular. But then they made Tranium 1 and Inferentia 2, which are actually basically identical chips, just with different numbers of networking interconnects. So anyway, this chip is 4 times faster than the original Inferentia. Then they created the Tranium 2, which was again 4 times faster, and they began deploying Tranium 2 at the end of 2024. Amazon is also currently designing a Tranium 3, which is supposed to start getting deployed at the end of this year, at the end of 2025. You'll notice I stopped talking about Inferentia, and that's because this year Amazon decided to cancel their Inferentia 2.5 and their Inferentia 3, which they had planned. I guess they thought their money would be in accelerating the training aspect of deep learning. Or potentially these training-specific accelerators were actually very good at inference as well, so they decided they didn't need to have 2 lines of hardware. But it's interesting because I remember talking to Groq and Cerebras, and both of them were betting a lot more heavily on having a lot of inference workloads in the future. Maybe Amazon decided that those startups already have a lot of specialized inference hardware and that they didn't want to compete on that front. Who knows? Let's talk a bit about the performance of these chips. I'll put a little chart on the screen, but I'm just going to talk about the FP16 performance for simplicity. The Tranium 2 has 667 teraflops of BF16 performance, which is basically like FP16 performance, while the Tranium 3 is rumored to be, of course, 4 times faster and have 2,668 teraflops of FP16 equivalent performance. When you compare these numbers to an H100 from Nvidia, specifically on the SXM interconnect, which is slightly faster than PCIe, you're getting 1,979 teraflops for FP16. So you need almost exactly 3 Tranium 2s to match 1 H100. When you look at the Blackwell chips, which are currently coming out from Nvidia, they are about 2,250 teraflops for FP16. That's for a B200 chip. Of course, you can get the GB200s where they combine 2 of those together, and hence you would get double the flops. But anyway, a Tranium 3, if it really does come out to be 2,668 flops, is actually a little faster than a Blackwell B200, which is really amazing for Amazon to have caught up to and exceeded that state-of-the-art hardware in a relatively short period of time. The reason Blackwell seems so much faster, by the way, is because you can combine 2 of them together, and you can also do computations at FP4 precision, which I guess is really good for inference. I'm not so sure you would do it at training time. Anyway, like I said, 3 Tranium 2s to match an H100, and about 4 Tranium 2s to match a B200. But the more direct comparison for Blackwell chips would be Tranium 3, because they're being released roughly the same time. Well, a year later for the Tranium chip. So let's talk about the architecture of the Tranium 2. Amazon's architecture copies what Google TPUs do, in the sense that there's a small number of really powerful cores instead of having thousands of really weak cores, which is what Nvidia does with its CUDA cores. Large cores are actually better for generative AI workloads because there's less control overhead. So that's why when you have more specialized chips like TPUs or Tranium, they are using larger cores. In each core of the Tranium chips, the cores are called neuron cores. There are 4 separate engines that do different types of computations. There's a tensor engine, which can do matrix multiplies and whatnot. There's a vector engine, a scalar engine, and a GP SIMD engine. The last is for general purpose computations, and it's actually arbitrarily programmable from Python or from C++. The first one, the tensor engine, is the most important. More than 80% of the computations that are going to happen in a modern LLM workload are going to be in the tensor engine. Another aspect of the design is how the chips communicate with each other. On Nvidia GPUs, they actually cannibalize some of the existing cores and repurpose them for communication. It's actually possible to configure the number of cores that are allocated for communication versus computations. And the optimum value could differ based on the exact structure of the computations you're trying to perform. It's a very advanced operation to tune this though, so most people don't. This was a really big part of the optimizations that DeepSeek performed, however. They were able to basically increase the amount of cores that were allocated to computation to make their locked down, restricted GPUs actually perform at a much higher level. But anyway, all of that's in contrast with what happens in Tranium 1 and 2 chips. What they do there is they have allocated special purpose cores just for communication. This is much simpler and potentially higher performance, but it is a little more expensive to pre-allocate portions of the silicon for communication. But nevertheless, seems like a good design choice here if you're optimizing specifically for generative AI workloads. When you're writing code for Tranium chips, you can't use CUDA, which is what everybody in the industry is familiar with. It's a big moat that NVIDIA has protecting its dominance in the machine learning space. But there are ways around that dominance. And I made another video previously over here, which you can check out if you like, talking about how the dominance of CUDA might be coming to an end. Anyway, on Tranium, you're using the Neuron SDK with a Neuron compiler, and kernels can be written in Python or C++, like I said, usually higher performance in C++, but very good option to have Python available as well. The other really interesting design point I want to highlight is a higher level one. Once you have these Tranium 2 chips, how do you put them together into a data center? Well, the typical unit that you think about in a data center are server units, right? Like a 2U server, for example, takes up 2 units of space, and the server normally is standalone. It has CPUs, GPUs, networking card, whatever you like. Then you have a rack, which has, 18 units or however many units there's supposed to be. And you have a bunch of servers in there and maybe like one router at the top to handle networking. That's the standard layout of computers in a data center. But what Amazon did with the Tranium chips is they realized that these chips are normally going to be used in large quantities. People are going to be training really large training runs at the same time. So they actually re-envisioned the entire rack as one computer. There's one 2U server, which has CPUs in it and connects to the general network. Then there's 8 other 2U units, which are compute trays. They have 2 Tranium chips each, but they don't have any CPU. Amazon's term for this is JBOG, just a bunch of GPUs. So it's really weird. You have these partial servers that have only GPUs in them. They have only the Tranium chips in them, and they're all connected up to a single head node, which is effectively the connecting piece of this whole rack scale computer. Amazon also created a new type of networking for this, very high bandwidth, which of course they called Neuron Link. And the standard configuration is that they take 4 rack servers and they connect those 4 racks with Neuron Link. So if you're keeping track, each rack has 8 slots where they just put Tranium chips in, and they put 2 Tranium chips per slot. So each rack has 16 Tranium chips. You put 4 of them together, you get 64 Tranium chips total. And they all work together in one world. In other words, it's like having Nvidia GPUs connected with NVLink, where you get extremely fast connections between the GPUs. Well, here you get that extremely fast connection between all 64 of these Tranium chips. And that is in fact what a Trn2 Ultraserver is. If you go to AWS right now and you look for Trn2 Ultraservers, you can rent them, and that's what it is. It's 4 racks connected with Neuron Link. Each rack has 8 times 2 Tranium chips inside of it. So all of this is really cool, but you do have to ask, did Amazon actually achieve its end goal in doing this? Because these chips are not produced by Nvidia, okay, that makes them cheaper and you're not dependent on Nvidia as a blocker for the supply chain, but they are all produced by TSMC, the Taiwan Semiconductor Manufacturing Company, just like Nvidia's chips are, just like every advanced chip in the world is, pretty much. But I guess if you need really fast, modern chip architectures, you basically have no other choice. So yes, a TSMC 5 nanometer process is used for Tranium 2, and they're planning to use a 3 nanometer TSMC process for Tranium 3. And interesting data point, although Tranium 3 is going to appear at the end of 2025, appear as in become available for some Amazon customers, Amazon is still producing a lot of Tranium 2 chips. In fact, although many were already deployed in 2024, in 2025, it seems that Amazon will produce 1.7 million Tranium 2 chips and make them all available in their cloud. What can I say? The market is getting interesting. Finally, in conclusion, we talked about Amazon's foray into producing AI accelerator chips. They've partnered with Anthropic, and they've convinced Anthropic to use 400,000 Tranium 2 chips to train their next Claude models. Amazon is doing this because they think they can grab a portion of that data center accelerator market, which is currently owned by Nvidia, basically, and because they want to have multiple suppliers. In fact, Amazon is being very careful to maintain a good relationship with Nvidia as they're doing this, right? They still want to have Nvidia GPUs in their cloud because Amazon, AWS, is the biggest cloud provider in the world. They have to have Nvidia chips. Amazon incorporated a lot of good ideas into their design for their chips, very similar to how Google TPUs work. But even though Google has had TPUs for a long time, they've had trouble kind of getting mainstream adoption. Amazon seems to be going very fast, pedal to the metal, 4 times faster every generation if they can manage it, and already offering some customers that use Nvidia GPUs from Amazon to take that same amount of compute and get it from Tranium chips instead and be charged only 1/4 of the price. So I really like Amazon's strategy here, and we'll see where it takes them. I do want to mention, however, that not everything is amazing with Amazon from my perspective. They still have questionable and monopolistic business practices in many areas. For example, there was an Amazon fulfillment center in Quebec, Canada, at which the workers were about to unionize. And Amazon decided to completely exit the province of Quebec. They shut down 5 data centers because they don't want to have to change the working conditions in their warehouses. They want to make as much money as possible. So I just wanted to add that caveat. I'm very excited to see where Amazon's AI accelerators will end up, where that will take them. But Amazon has many different departments and areas in which they do business. And in some of them, they are taking profit above the well-being of their customers and their employees. So still work to be done. Well, if you liked this video, check out this previous one I made where I talk about the factors that have led to Nvidia kind of dominating the GPU market with an emphasis on CUDA and analyzing how sound the CUDA moat actually is. If you liked this video, I'm sure you'll like that one too. And if you'd like to see me do a deep dive into other types of hardware, please leave me a comment. Oh, and one other thing. I've started posting a lot more on Twitter or X, and also Bluesky, and also Substack. So go ahead and follow me on one of those other platforms if you'd like to see some text-based content every now and then. Well, I think that's everything for today. Thank you very much for watching. Bye.